If I show you this little container, it's not too hard to figure out that there are in fact 3 red blocks and 2, 4, 6, 7 green blocks. And I think you can see there's in fact no more there. So in fact, in that little container, the proportion of red blocks is in fact 0.3. If I show you this container, I think you can see that if I asked you to figure out the proportion of red blocks, the job's a little bit more difficult, and you'd have to probably open it and tip them out and count them out. Absolutely possible to do. Laborious nonetheless, but you could do it. If I show you this third container that you've got to imagine, if you could imagine this container that was full of the about 110,000 registered voters in the federal electoral district of Brisbane, if you can imagine that box, and we were keen to know the proportion of red blocks. So we'll use red blocks as a bit of a metaphor here. In that particular group or population, maybe it would be the proportion of people who might vote Liberal or National, Labor, Green, whatever. If we're interested in the proportion of the red block, how would you figure it out? Well, of course you could get them all, come on down, and you could tick them off and measure, ask them, but big job, and of course costs a lot of money, and that's not commonly, as I'm sure you're aware, the way we do it. We do it by a poll or taking a sample. And so what we're going to do is have a little journey this morning and look at a way to think about a confidence interval for a proportion, which is in fact the tool that tells us something about the proportion of red blocks in a population without us having to open the lid and count them all out. And we're going to do that through this idea of sampling, and we're going to take we're going to get this idea in our head where we go out and we take some sort of random sample out of this population, and we ask them who they prefer, they tell us, and from that proportion, which would be the proportion in the sample, a confidence interval proportion tells us we can figure out something about the proportion. So there's kind of two values we're interested in here. There's the value of P, which is what we're going to call the proportion of red blocks in the population, and there's P hat, which is the proportion of red blocks in the random sample that we take. And so they're the two sort of quantities that we're going to think about. And the only way really I can figure out to understand sampling is actually to do some sampling, and to do some sampling with a population for which we know the proportion of red blocks in the population. Do that sampling and see if we can study the effects. What can we learn from actually sampling and looking at the results? So that's what we're going to do, and we're going to do it with a little help from a little computer or a little calculator. So there he is, and I'm going to hop into the Run Matrix menu and call up a little command from the option menu, and then the probability menu, random menu called ran number, which I'm sure you've probably seen before. And if I press execute a few times, then the little computer is basically dealing me or delivering me a number that is been dealt to me on a sort of like a pseudo-random kind of basis. In other words, I can't predict what's coming. I've got no way of knowing for sure what's coming next. And it is producing for me numbers between 0 and 1. So if I write over here, this little command ran hash is producing numbers 0, 1, not 0, not 1, and it produces them in a uniform manner. So I can expect 0.1 just equally as much as I can expect 0.9, blah, blah, blah. And that's what that little guy does. So somehow I'm going to turn this thing into a sampling process that can in fact help me to study what happens if I draw samples from a population. So this is what I'm going to do. I'm going to ask firstly the machine to integerize these random numbers. So if I integerized, what would happen if I integerize them? Well, it chops off all the decimal places, so it would just give me zeros. And of course, that's not too helpful. So I'm going to get it to integerize this. So go back to my probability menu, and I'm going to say, machine, could you please integerize for me 0.3 plus, not rand hash or rand number, but list, which is a command that does exactly the same thing as rand hash, but it gives me a list of numbers. Because if it gives me a list, I could put in something like 100, and that would be like choosing a sample of 100 critters out of whatever the population that this little piece of magic is creating for me. And so just finish that off, and if I press execute, with a bit of luck, it'll give me a list. And in that list, we should have, yep, exactly 100 values, and some are zeros and some are ones. And I guess it's not all that obvious, but we can reason that because we added 0.3 to our command, we're now generating numbers from the range 0.3 up to 1.3. And all those from sort of 1 to 1.3 onwards will end up being ones, and the rest will be zeros. So that's telling us that we've got a probability of getting a 1 of 30% and 0 of 70%. And so this little thing is basically now taking a sample of 100 critters out of our population, where the proportion of red blocks, or people who vote for whatever you want to think about, is 30%. So I guess I'd like to know the proportion of ones in that list. So let's see, what could I do? I could come back here, and I could just sum up that list and then divide it by 100, and that would give me the proportion. So to do that, I can just go into the option menu and then my list menu, choose sum, and then I want to sum up this list result, which I can do by saying, could you please sum up for me shift list, and get me the answer option down here. And that tells me that there were 28 ones in that list. Well, I don't have to divide by 100. That means my sample proportion in this case is 0.28. So beautiful. Now I could of course do that again. So if I just put my little cursor up onto that first line that I want to be recalculated and press my result, I end up with 31 ones that time. So proportion of 0.31, just come up here again and press that again, 28, and so on and so on. And the object here would be to do this lots and lots of times and kind of see how these proportions vary over many cases. So to help with that, I made a little program. Instead of pressing every single time. And the little program looks like this. So I'll show you the code first. And it just does some things, clears some lists and so on. And then the heart of the program is down here. Yeah? And you can see that it says, get the integer value of some number plus rand list, give me so many and shoot that into list 1 of the statistics menu. So in this particular program, I can set the population proportion P and the sample size that I want to take. Then it just sums up the list and divides it by n, puts that in list 2, and there's a little while command here, which means it just keeps doing this for as many times as I like, so I can collect as many sample proportions as I like. Now, of course, in real life, you can't do that, right? In real life, you go and you get one sample proportion, but in our little study here, we're going to do it over and over and over again. So let's give it a go and see. I'll exit from there and I'll execute the program. So it says, what's the population proportion? So we'll stick to 0.3. It says, what's the sample size? Well, we'll take 100. So sample size 100 and execute that. And it says, how many samples would we like? Well, I don't know. Just for now, why don't we just take 50 and just see what happens. So let me just summarize, and you might not see this on the board yet, but when we go back to the board, you'll see it. So what we're going to have here is this notion of, we know P is 0.3, and we're choosing a sample size, which is normally denoted N, to be 100. And we're gonna, this case, take 50 samples, just to see what 50 sample proportions, just to see what 50 sample proportions are going to look like and how they vary. You know, are they all 0.3? Are they wildly different from 0.3? So here goes, we'll execute that, see how long that takes. 1,000, 2,000, 3,000, 4,000, so I don't know, about 5 seconds or so. And if we pop back into menu and into our statistics, bingo. We've got, this is the last sample of zeros and ones. And we hop up to number 1. That was the sample proportion, or p hat, of our first guy. So let's have a look. That's going to be 0.25. So in our first go at this, we've got like a p hat of 0.25, and then our next one is 0.32, and then our next 100 returned a sample proportion of 0.26, and our next one 0.24, and I think you get the idea. We can zip down here. And of course, I guess what we want to do now is say, maybe take a look at these and see how they're distributed, how they vary. And we might do that by drawing a histogram of list 2. So let's draw a graph. And we'll draw a graph, we'll set up a graph, make sure it's a histogram of list 2. That's good, already there. So exit from there and we'll draw our graph. So of course, the sample proportion is going to vary from 0 up to 1. And I think I saw some, 2-digit numbers there. So let's go in steps of 0.01 and see what happens. So that's good. Let's execute that. And pow, there's a picture of our variation of our sample proportions. So on that x-axis, let me just stop sharing for a minute. So on our x-axis here, we've in fact got the quantity p hat, or the sample proportion. And if I go back to my machine, here we go, you can see what that looks like. So if I trace that guy, you can see that I ended up with no sample proportions down the very low end, like 0.9 or 9% red blocks. None, none, none. My first low value was 0.19 or 19%, which you can read there. And then you can see I've got quite a few, about 8.26s, 5 of them, 0.27. Where's the, we know the population proportion in this case is 0.3. We didn't get so many of them. That's interesting. And then we got a few less of those. But of course, with, what do we get here? 50. With 50 of these, we're probably not going to get the best, most robust picture of how these values vary. So maybe we should up that a little. We'll stick with 100 as our sample size, but we'll up the number that we get. And I guess you could start to think about what this might look like with more samples taken and more sample proportions plotted. So let's give it a go. We'll go back to our program. Find that little program. There he is. Execute him. So we'll stick with 0.3 as our population proportion. We'll stick with 100 as our sample size. But number of samples, we'll up at this time to say 200. And this will take a bit longer because the process is going to do its thing, but it won't take too long with a bit of luck. So here goes. So I think by the time I counted to about, I wonder whether it would be, might be 4 times as long, so it might be about 20 seconds actually, would be my best guess. And expecting it to finish right about now. Oh, I got close. So there you go. So this time we're going to have 200. So I guess that plot is going to kind of like fill out a bit. Let's see. So we'll go to number 2. There's our data again. So remember, list 1 would be our last set of 100, our last sample of 100, and this is our first sample proportion, the proportion when our second sample, third sample, and so on. So we'll just go straight to our graph. Let's have a look. And so that's filled out even a little more, and I guess it's clear to see what's going to happen here. We've got very low chance of getting a very low sample proportion, and it looks like the chances of getting something around, well, there you go, look at that. So this time the chances of getting something around 30% are quite high, and they level off as we go out further and further and further. So what we'll do is we'll draw a little picture on the board, and then while we're doing that though, we might set this machine running. Let's see if we can do this. We'll set this machine running, go back into our little program, and set that to be 0.3. Sample size 100 again. So last time we took 200. So let's this time go to 500. We'll just sort of build it out a bit more. And we'll set that running. And while we set that running, we'll come back to the board. So in fact, I'm guessing you've already got half an idea or maybe a full idea of what happens here with this, but the more and more you take, the closer and closer and closer this guy's going to come to some sort of shape that you're pretty familiar with, which is the normal distribution. And there's some lovely maths that underpins the fact or why this is so. And of course, it's rooted in the binomial distribution. And in this story, we're not going to talk about that. So we're not going to talk about the road of how the binomial distribution, in fact, leads us to be able to say what we're about to say. We'll leave that for another day or another story. So what we can see is that this shape looks like it's appearing, and in fact, the mathematics tells us that it does. And in fact, the mean of that guy will in fact be the population proportion P, which for us at the moment would be 0.3, and that it will have a standard, a sort of a variation value or a standard deviation value. And of course, there'll be roughly 3 standard deviations going out here. And the standard deviation of this guy, oh, by the way, this guy here, P, would be called, in fact, it would have a name, it would be mu, mean, mu of P hat. And the variation of this guy would be sigma of p hat. And that guy is in fact equal to, I think it's equal to something like this. It's equal to p by 1 minus p all over n. And then it's the square root of that guy. And in fact, this guy's more correctly called, I guess, a standard error. And this guy, this whole bizzo, is in fact called a sampling distribution. And it's called a sampling distribution because it's the distribution that describes what happens if we repeatedly take samples. We know that the mean of the sample proportion will end up being p if you did it infinitely many times, and the way it varies is according to this little guy here, the square root of p by 1 minus p all over n. So that's our sampling distribution. So let's go back now and let's see if our machine has done its job. Well, he's still cranking there, as you can see. So let's see, what do we do? 220 seconds. So maybe 40 or, oh, there, oh, beautiful, there you go. So he's done. So now we'll zip back to our stats menu, have a little look. I think we just go straight for the graph and same story. And oh, pow, there you go, look at that. So it's starting to really take some beautiful symmetrical shape. You can see we've got one interesting little peak there. But of course, we've only taken 500 samples. And I guess we should have a little look at the statistics on that guy. And it'll compute and tell us that the sample mean, or the for this particular set, the mean of all those 500 is pretty close to 0.3. So that kind of supports what we're talking about back here. And we could do a little bit more thinking about this variability, but we'll leave that for another story. So there you go. So now we've established this notion of a sampling distribution. So let's just stop that guy. There we go. Come back to our board. Okay, so what next? So what we've done is we've done a study of sampling, and we can sort of understand now the way that these sample proportions will vary if you repeatedly sample. So if you repeatedly sample, we get the idea that they'll vary something, well, not something like, they'll vary like that. So let's go to our bigger problem where we actually have a population with an unknown proportion of red blocks. So this is sort of our main game now, is to start to think about this notion of, so we've got a population with an unknown. We've got a population with an unknown proportion, which is P, of our red blocks. And you can think about that proportion to be whatever you want. Doesn't matter. You can be the voters, or it can be a massive room full of these guys, which you don't want to count. It doesn't matter. And so how is it that we can actually learn something about this unknown population proportion by taking just one sample? How does that work? Well, firstly, we're going to take one sample from our little machine, and it's going to be one sample from a population with an unknown proportion. So in other words, I'm going to do this without you being able to see it. So just let me get my little machine, which you can't see. So you're going to have to trust me here, but I think you'll see that I'm doing a genuinely good thing here in a minute. So here goes. I'm going to open up my little program, which you can't see. I'm going to run this guy, and I'm going to put in a population proportion that you don't know. I'll know it, you won't. So here goes. The sample size I'm going to keep the same. We're going to take a sample of size 100. And this time we're just taking just one sample. And I'm going to press execute. Okay. Now I'm going to write down on a piece of paper the proportion I put in, just so that there we go. So I've written that down so that we can get back to that later if we need to. And now I am going to share my screen. Here we go. And we'll pop back into our stats menu, and you'll see bingo. There, in fact, is our very lonely single sample proportion, 0.76. So 0.76. So here goes. Let me unshare that. Okay. So taking just one sample, I got a sample proportion of 0.76. And the question is, what is that unknown value there? And let's just get that down there like that. Beautiful. Okay, so, well, here's, I guess, the what I think is the really beautiful logic of this story. So here goes. Let's draw an axis here. And that axis will be for our sample proportion. They're just the same as this one. And I guess the question is, where is this 0.76 along here? Is it really close to there? Is it over there? Is it over there? Is it here? Did I get really unlucky? Is it right down here? Really unlucky the other way, over here? Or in fact, did I get right on the mark? And in fact, the magic unknown number that I put in was in fact 0.76. And of course, we don't know. We simply don't know. So I'm going to suggest we do this. We just put it on the axis. And then we make the assumption that we got really unlucky. This, in fact, was really, really, really unlucky. And in fact, it was all the way down here. So I'm going to draw a sampling distribution above this axis, assuming that I got really, really unlucky down the low end. But equally, I could have got really, really, really unlucky down the high end. So I'm going to actually draw another distribution over here. And this is going to represent the almost unluckiest case down that end. And this is going to represent the almost unluckiest case down the other. So we'll call this 1, we'll call this 2. But from our little piece of theory over here, we know that in fact, if this was the situation, we know the true or the population proportion would in fact be there, even though we don't know what it is. But if this was the case, we know that the population proportion would be in fact there. And so what we can create with this logic is in fact an interval, and an interval that is centered on this guy, p hat. And I guess it depends on what you think of almost unluckiest, but that to me, kind of conjures up the notion of roughly three standard deviations, or three standard errors, if we want to use that term. Whoops, oh, out there, 1, 2, 3, that'll do. Be good if I could third things. And so in fact, there'd be approximately, or roundabout, or whatever, 3 standard errors here, and there'd be 3 standard errors here. And so what I could then say is, if I took 0.76 and I was to add 3 of these guys, and if I was to get 0.76 and subtract 3 of those guys, then I could say that the true proportion, the actual population proportion, lies within that interval, or actually more correctly, that interval actually captures the population proportion. And this one would end up being called, a 99.7% confidence interval for the proportion. If I wanted it to be a 95, well, actually that 3 is approximate, isn't it? So about that. If I wanted it to be a 95% confidence interval, then of course that would need, this number here would need to be 2. So I'd be kind of thinking that I'm not as unlucky as I was, and that would shift this way and that would shift that way. So in fact, we can do something like this now, where P will lie in between whatever the sample proportion you got was, plus some number of these guys, and the sample proportion minus some number of these guys. Oops, let's do that. Beautiful. And this would be our confidence interval. Now, if this was 2, then we would have an approximate 95% confidence interval. I guess it should be 1.96 to be a 95% confidence interval. And I think you can sort of figure out the rest of the stuff associated with that. So one last thing before we leave this. I could in fact do this again and get a different value here. And I could do it again and get a different value from here. And I could do it again and I could get a different value from here. So in fact, I could create as many of these confidence intervals as I choose. And the logic here is that on average, out of say 100 attempts, in this case, 99.7 of them would capture or fall over or include the proportion that is the population proportion, and the other percentage would not. Every time I do one of these, I get a different one of these. Every time I do one of these, I get a different one of these. Every time I do one of these, I get a different one of these. So on average, in this case, if this was 2, then 5 out of 100 in the long run would not capture the proportion, and 95% would. Okay, last couple of things to think about. If we don't know P, then this formula is a bit problematic for us because it's got a P in it. And so in your course, most likely what will happen is that you'll replace that with P hat. And what that means is that this confidence interval you create will be an approximate blah, blah, blah confidence interval. There is a more formal way to deal with that, but that's a story not for now. The other thing we haven't talked about is this value n. We're sort of stuck to a sample size of 100, and we could have talked a little bit about, well, what would happen if you chose to change the value of n? What if you take a small sample? If you take a sample of 10 versus a sample of 100 versus a sample of 1,000? And I'm guessing that you've already started to think about the fact, given this formula, that this will reduce in. And of course, that makes perfect sense, because if n was in fact the exact number of items in the population, then obviously this thing would, and you'd have no variability in the value, and you would actually get that population proportion with that one sample. So there's a way to think about it, and it leaves a few things open for maybe another day. How does the binomial distribution actually show us that this is in fact valid and makes good sense? We didn't look at n, what happens if you change n. We haven't really talked greatly about this p-value and whacking in the p-hat in its place. And we haven't really nailed what this thing means. I bumbled around a bit over that, I think, but I guess I should just end by saying what this doesn't mean. In fact, I suppose we should do the computation for this, shouldn't we? We should actually do that so we can see that. So let's go back to our machine. This is probably a good place to finish. So if we wanted to do that computation, we could, of course, just plug the numbers into that formula, or we could get the machine to plug the numbers in for us. So we could come back here to our stats menu and go into our interval menu, a Z interval, one sample, oops, back out of there. Let's do that again. Interval, Z, one proportion. And in here, we could say a 95% confidence interval. This says how many red bricks did you get, or how many red blocks, and we got 76 in our case, and sample size 100. And if we compute that guy, then it tells us this interval is in fact going to be between 0.676 less than or equal to 0.844. So let's just come back to the board. Can we see that down the bottom? Yeah, we can. So this is probably the last place to finish. And I did bumble over this a bit, I'm sorry. And what does that thing mean? And there's a couple of statements that often come out with this, and maybe we'll make another how to think about this later to help out a bit more. But often people will say, well, there's a 95% chance that the population proportion is in between these two values. And that is technically not correct. It is technically correct to say that there's a 95% chance that this interval captures the population proportion. And the reason that those two things sound so similar but different is just come back and think about the fact that we could have repeated this over and over. Every time we would in fact get a different sample proportion, and every time we would get a different confidence interval. So every time we did this, we're not getting the same interval, we're getting a different one. And so the logic is there's a 95% chance that any given interval will in fact capture the proportion. There's not a 95% chance that the proportion is in between these two particular values. And we might sort of piece that out a little bit more in a later story. So I think that's probably a good place to stop. that was the number I put in, interestingly. And interestingly, our sample proportion got pretty close first time off. I'm hoping one day I'll do that and I'll get something really odd and we'll get one of these intervals that in fact doesn't cover the population proportion, but it wasn't to be today. Hope this was useful to you, and we'll see you again.